In this video we study an interesting theoretical concept in distributed systems, namely random oracles. Before we define what a random oracle is, let's look at a motivating example. Let's assume that the nodes in a distributed system must agree on some data. In the simplest case, they need to agree on a single bit. Each node has an initial value. How can the nodes agree on a single bit? In the message passing model, the only way for nodes to interact is by exchanging messages. In the example here, every node sends a message to all other nodes, informing them about the node's current value. Without specifying a concrete algorithm, let's just assume that the nodes decide that there is no agreement based on the received messages, so each node simply flips a coin and sets the local value to 0 or 1 depending on the outcome of the coin toss. It may happen that all nodes randomly set their value to the same value, for example, 0. Now, reaching agreement is quite simple because all nodes share the same value. This simple strategy can be used to build correct algorithms, but it has a significant drawback. The probability of all nodes randomly choosing the same value is exponentially small in the number of nodes. This means that the nodes need to repeat this step a number of times that is exponential in the size of the distributed system. Clearly, this is not practical for larger networks. The problem is that each node uses its own random coin toss. Instead of doing so, each node could use a so-called random oracle. A random oracle provides randomness, that is, unpredictable bits, but in such a way that all nodes always receive the same random bit. In the example here, the random oracle provides the random bit 0 to every node. If all nodes adopt this random bit, all nodes immediately agree. What does that mean for the number of rounds? Assuming that the algorithm requires a constant number of rounds before the oracle must be queried, then agreement is reached in a constant number of rounds, even if the nodes only agree on the value provided by the oracle with a constant probability. While this sounds great, there is a big problem. Such perfect random oracles don't really exist. Can we build something that comes close to a random oracle? One could simply use a random number generator to create a random bit string. We can then give this bit string to each node as a replacement for a true random oracle. So, we emulate a random oracle by having each node use one bit after the other from the shared bit string. Is this a good solution? Do you see a problem with this approach? This is a good time to pause the video and think about it for a minute. Did you figure it out? There is indeed a problem because giving each node a fixed bit string means that the algorithm is actually deterministic. There is this famous result that says that consensus cannot be solved at all using a deterministic algorithm in the asynchronous communication model where messages may be delayed indefinitely even if only one node may fail. Let's take a look at an example that gives some intuition as to why our approach with a shared bit string doesn't work. In this example, all nodes except one have value 1. The next bit in the bit string is 0. Let's consider the following simple protocol. In every round, all nodes exchange messages. We assume that a node implicitly sends a message to itself. We further assume that the algorithm can tolerate one node failure, that is, every node updates its value once it receives 4 messages. Specifically, if a node receives the same value in all 4 messages, then it sets its value to the received value. Otherwise, the node uses the next bit from the bit string as its value. The current value is then broadcast in the next round. In the example, all nodes broadcast their values. We assume that the messages of the node at the top are slow. The messages have a lighter color so that they can be identified more easily. Each node receives the messages from the other nodes. However, all nodes except for the one with value 0 do not receive the slow messages in time for their next action. As we can see, only the node with value 0 receives 4 messages containing value 1 and so it sets its value to 1. All other nodes receive 1 at most 3 times and so set their value to the next value in the bit string, which is 0. For the next round, each node will then use the next bit of the bit string, which is 1. However, we can now see that we are in the same situation as before, simply with all zeros being 1s, including the next bit of the bit string, and all 1s being 0s. It is easy to see that we can now continue this game and the algorithm will never make any progress. It is important to see that the algorithm fails even if there are no node failures. It is enough to define an unfortunate order in which messages are received. Note that we didn't really specify the algorithm in detail. Specifically, we didn't define how termination would be detected, but that doesn't matter. No matter how we define the algorithm, it is not possible to reach agreement. Let's summarize what we've learned. We introduced the notion of a random oracle, which is a powerful tool as it allows us to solve hard problems such as reaching agreement efficiently. We then looked at a simplistic approach to implement a random oracle using a shared bit string. Unfortunately, this approach makes the algorithm deterministic, which defeats the purpose of a random oracle. We conclude that a more elaborate mechanism is needed to approximate a true random oracle. Thanks for watching.